Hello and welcome. Today I'm going to start a multi-part tutorial series or maybe some kind of journal of building an AI computer improviser using Max MSP, which will incorporate a few external libraries, namely ML Star by, I think it's Benjamin D. Smith, and the Flucoma library. And Flucoma is a project that integrated machine learning algorithms for audio analysis and buffer management and all sorts of interesting things into Max MSP, as well as Super Collider, and I think Pure Data as well. And that came out of the University of Huddersfield. It's a recently completed research program. In any case, today we're going to build what you see on the screen here. It is going to be the first step. What I have on here, I'll just show how it works. We'll open up a piece of audio. It's going to be a 2-piano piece of mine called Distances. And it will automatically trigger an analysis based on MFCCs. That will be able to sample back. And we can query either plotter. So there's a plotter that's been made into a grid, and then one that is just the raw output of a UMAP dimension reduction on the left, both of which can be very useful. Played back through this sampler that I made in Gen, which is the subject of an earlier tutorial that's on this channel, which takes the note start time, end time, gain, speed, and then the window shape. We'll close this and we'll build it up again. So we're gonna keep this already. I'll just open it up if anyone wants to copy the code. So this is the subject of an earlier video, as I mentioned before, but just so it's on the screen, and then you can also see what is inside the Gen. And then there's also even a Gen subpatcher here. So there, it's all appeared on screen now, I believe. So if you want to copy it out that way, you will be able to. And then inside here is something that will convert, a simple patch that will convert a stereo file into a mono file for the purpose of analysis. Okay, so we're calling the buffer corpus 1. Okay, so now we're actually going to want to create a new patcher, and we'll call this MFCC grains. So we're only, rather than slicing at attack points, we'll save that for another video as well. We're just going to do analysis by grains. Could be of any duration. So it could be 100 milliseconds. It could be, I guess, 3 minutes, but we won't do that. It's a very long grain. So we'll call it MFCC grains. Start by creating an inlet and an outlet. Oops. And then save that. I'm actually going to close it. And then I'm going to create MFCC grains. And I'll give it no arguments to start. And we'll actually build it as a modify read only, which is a bit precarious. You don't want to save this patch before this one, or else it will overwrite sometimes with without the changes that you've made that are sort of live in here that you haven't saved yet. So you got to be careful when you're doing it that way. Okay, so within MFCC grains, we want to have access to a few arguments. We'll want to just have a name. So MFCC grain can be our name. And we will want to have the name of the audio that we're going to analyze. So we'll call it corpus. You know, I'm just going to, for the sake of not duplicating things, I'm just going to, instead of corpus 1, it's just going to be corpus. That should work. Let's load some audio in and make sure that it does it properly. Great, so we have our mono version there in the corpus 1.mono, and we have our unmolested 2-channel version there in corpus. So when we play back samples, we'll play them back in stereo, but when we are doing the analysis, we'll play it back from the mono file. Great, so here we want to have corpus and corpus playback. Great. So we want to be referring to our corpus.mono for analysis. And we are going to want to have our grain length. Let's do 1/2 second. And we're going to want to have the number of labels that are used. So those were the colors that you saw in the earlier one. So we know already that we're going to want to have all that data be in particular to this analysis. Let's have a bang here. And we can go ahead and go back in here, modify read only. And now we can start with the MFCC analysis. The basic analysis object is fluid.buff MFCC. So this will look at the MFCCs from a file, so the Mel frequency capsural coefficients as spectral descriptors, and it will use a buffer to store that data in various ways. So we need to cook this data quite a bit, but we'll start by saying we want 30 of the coefficients. The source is going to be the buffer, so that is our first argument. We want, for the starting the first coefficient, we want to skip over the 0th coefficient because that's just loudness. And we want to only use one channel because it's a mono file. So although that is probably not necessary to include, just in case. Okay, so now we need to tell it what the start and end point of the analysis is. So it could analyze the entire thing, but that data won't be very useful for us. So we need to give it chunks of data and then cook those chunks of data so that we have these points that that have sort of relevant timbral differences that are kind of allow us to organize them into groups of similar sounding grains. So we'll give it a start frame, and we'll give it an end frame. Oh, sorry, not end frame, sorry, number of frames. And in fact, for that, that's going to be determined by the argument. We can do load mess and then the second argument. I believe this will work. And then prepend num frames. And if we do that into the right inlet, in fact, we want the third argument, and our source should be the second argument. There, okay. There you go, num frames 500, perfect, that's what we want. So from here, this doesn't need to be, oh, whatever, that's fine. Okay, so this is gonna give us our grain size, so this will be useful data to have. Okay, so this is, and then we're gonna have a bang here, which will actually do the analysis, though I don't think we'll necessarily need the bang object. In fact, we can go ahead and go trigger bang. That'll be the last bang. We'll need the integer of the start frame, and we'll need to bang out the number of frames. So it'll be number of frames, integer giving the start frame, and then bang the actual analysis there. So we'll want, we need to first get the total number of samples in our corpus audio file, and then divide that by the grain size, which will give us the number of bangs that we'll need to send to an Uzi to count through, and then we'll change the start frame, that number of times. in order to analyze grains of the entire sound file. So we're going to start with trigger bang bang because basically the right bang will clear previous analysis and the left bang will be used to actually do the new analysis. So for now, we want info on our buffer, which is MFCC grain, or sorry, corpus.mono. And then we want milliseconds to samps because it gives our length in milliseconds there. I'm going to get a little more space here. Hold on. And then we want to divide by, and I'm just going to put that, so that's 1 second in samples, just as to have something there in case, I don't know, it's initialized incorrectly or whatever. So for this, we want the millisecond samples to go in, go in here. We'll also want a milliseconds to samps of the number of frames, and that will be what it's divided by. Great, so let me load nest that again. And now we need to get it to the Uzi. So for the Uzi, we'll want trigger, so to bang out the Uzi, and then we'll need the integer for the number of bangs that it's supposed to give. And hold on 1 second. Great. So for this, we want our Uzi. And so that's a number that's actually bang it out. Now we'll need a counter. That will go into here. That will go into here. And we'll want to, again, you will use this to reset the counter. So that basically clears everything we did previously. And then from the counter, we want to multiply the count. Each time it's counted, we want to increase it by our grain size. So again, I'm defaulting to 1 second, but we'll just give it our grain size that way. And then from there, I think it's directly into that. So we're asking it to do this in rapid succession. So if we did it now, we would basically just get the data for the last grain. So what we need to do is cook this data and store it in as points in a data set, in the fluid.dataset object. Once again, all these fluid objects are part of the flucoma library, which is available in the package manager. So we want fluid.buffer stats. So we'll get the look at the statistics and average out the data in each grain. And then we want to send that directly to, we want to flatten it so that it's all in a single channel. Fluid.buff flatten. Good. At num frames 1. Okay. And then from here, so this is the data that now we now want to store into a data set. So for that, we'll need a counter, and we'll want to do well, we'll want a data set, so we'll call it fluid.dataset, and it'll be the name of our buffer and then data. And now for each one, we'll want to add point. So I'll add point, and then it will be $1 from the counter, and then it will be, we'll need to get the second bit of data, which is the name of the buffer that it's adding the point from. Everything is with buffers in Flucoma. Okay, so again, we want to make sure that we're not just writing more and more data. So we want to clear it every time we do a new analysis just before. And we also want the counter to reset just before every time as well. And here we'll want to join two pieces of data, which are the count hold on, this is getting very long. Let me just move this up. Oops, move this up. So it's the count and the buffer name that comes out of buff flatten. So for that, what it's going to give is buffer, then buffer name. So we just need to add one of these guys. I suppose we could use a sprint F for this as well, but I think this will work just how we want. And then this will bang the counter. And that should get the data set. And just as a sanity check, we can have a look at our data too. So we'll want there, and we'll dump our data out. Great, and so let's try it. There it is. So we see 30 columns. So those are the 30 MFCC coefficients. And then we have the data there. And you see the numbers range wildly. And our next step is to standardize that data. But this is a nice sort of self-contained bit of analysis. Actually, hold on. I want to keep this. It's always good to be able to see it. So what we're going to do here now is encapsulate all this and then work on the next part. Okay, so we'll encapsulate all this. And we'll say this is the MFCC analysis in the subpatcher. Okay, so now we'll need a trigger bang bang, and we'll know that's the first step that we want to take when we send a bang in. And then the second step will be to standardize it and reduce the 30 dimensions to 2 dimensions so we can plot it on a fluid.plotter on a 2D plane. So for that, we'll need fluid.standardize, and this needs a name, and we'll give it the same name as the first argument, MFCC grain. And then we can't just bang it, but we need to actually transform a data set. So for that, we'll go fit transform, and it's a data set that we were just looking at. So I believe we called it name data. Let's double check that to make sure. Yes, there it is, number 1 data. Great. So first argument data. So if we put that in there, bang it out, that should standardize that data. And then from there, we want to reduce that data to 2 dimensions from the 30. So for that, we use UMAP, and we want the number of dimensions to be 2. So we can put it on the 2D plotter. Num neighbors, I'll put it 5. So that's the number of sort of nearby data points that it considers when it's organizing itself. And then I want to set the minimum distance at 0.9 so that things aren't too clustered together. So those are values that I've used based on just my experience, just heuristics. But there are, I would encourage you to sort of mess around with all the flucoma objects to figure out how they work, how they feel. All right, so now we want to normalize this data so that we can plot it between 0 and 1. So I believe we just need fluid.normalize and connect it right into there. It used to be that you needed separate buffers for each of these, but now it manages the buffers automatically, which is really nice. Now what we're going to want to do is save this data in a data set, as well as fit it to a KD tree, which will then allow us to look for nearest neighbors in the data and callback samples. So for that, we want the symbol. So if we go fluid dot dataset, dataset, and we call it number one. Yeah, we can just give it because this is our main data set that we're going to be referring to. So we need to now refer it. So basically copy the data over to this data set. So we go, oh, sorry, not number two, $2. So out of here, it will say buffer, then the generated buffer name. So we're referring it with the generated buffer name to that. For the KD tree, we need to fit the data. So we're going to fit and then refer to that buffer name. And this doesn't need to be in any particular order. So I have it both come out with the same symbol. So fluid.kd tree, and we'll name this the first argument, and then this is our two-dimensional tree. Connect that in there. So that should do it. Let's grab this stuff here to make sure that it works. All right, so let's see if we bang this, if it does all the analysis that we want. There it is, reduced to 2 dimensions and normalized. So from here, we can already do the plotter. So if we do fluid dot, plotter, we can plot the data in 2 dimensions by, I believe, just sending it like that. Let's see if that works. Oh, and we'll need to dump it. Oh, and we'll need to send it out there. There we go. Beautiful. So I want it to dump out automatically. So that can be done using that. Bang, there. Great. So we'll get a slightly different thing each time we do the analysis. Okay, so that is our major second step completed. Let's already make it so that when we press this plotter, it will highlight what we're playing back. So for that, I'm gonna want to have a speed limit on how fast the data is coming out of the plotter. And then I'm going to want to have an inlet to bring the data back in, and it's going to go to this KD tree, so we can just put it near there. Okay, so now in order to query this KD tree, we want to send it the message k-nearest to find the nearest data point to the one that we're giving it. Yes, I sort of know already ahead of time that we're going to want the second thing coming in. So let me hook that up there. Now, coming in here is just the XY coordinates. And what, so you see there are the XY coordinates. And what we actually want is to store these coordinates in a buffer and then refer that buffer. So again, buffer name, that's why it's number 2 there. You want to store these coordinates in a buffer and then refer to that buffer with the k-nearest message. So if we had a buffer called point, then we do k-nearest point and it would look at that buffer. So we don't want just a buffer with a single sample in it. And because of the automatic buffer management that Flucoma has developed, all we need to do is fluid dot list to buff, and that list of 2 items will be stored in a buffer that's automatically given a name. So if we look just sort of show how this is working again, right? So now if we go k nearest that one, then it'll actually give us the result of the query, the closest data point there, right? Great. Now let's delete those. We don't need them. One thing I want to add to this is number of neighbors. I want to make it 5 so that we can, if we sort of are dragging around the same area, it's not just hitting 1 or 2, but it's hitting, sort of cycling through 5 different fits. Oh, we need to refit. So we need to refit the data because I reinstantiated that there. So let me just redo the analysis there. And now, yes, there we go. So k nearest, and then the list of the 5 nearest data points. Okay, so from here, we're going to need to interpret that data. So for that, we will want to, route k nearest. And then from there, we'll want ZL nth 1, 2, 3, 4, 5. Will that work? No, I just want 1. We'll have to have different for each ones. All right, so 1, 2, oops. Why is it doing that weird cutting off the side of it there? I'm not sure why that's happening. 1, 2, 3, 4, 5. Great. Now we want from symbol for each of them because it was in quotations in a symbol as a symbol. We want the integer. There we go. So now we'll have our integers, and then we want to cycle through all 5 of them. So we'll want it to cycle to the next one if the first one is a repetition. So one way to do that will be to use trigger int to a select object. And then we'll want to cross them like that. And so if it's a repetition, we'll send a bang. And if it's not a repetition, it will forward that data. Okay, so if I have my cycle object 5, then for the repetitions, I get bangs. So it'll cycle through. And so then I want to store all these things in integer boxes. So it'll be, oops, from symbol, store the value, right? Okay, so write inlet, storing the value, and then cycling through with banging out those values like so. This is all just to avoid repetitions. So this, like this, this, and then this. All right, let's see if that works. Good. Excellent. Perfect. Okay. So from here we have, we want to prepend highlight. So we highlight it in the plot. Did I spell highlight there correctly? That's like height light. Hold on. Prepend highlight. Now I believe if we now send that out to the right inlet, of the plotter, then we will get, yes, if we need to send it out to the right inlet. All right, so we want the second one here. So let's just add a comment. It needs to be a symbol. So let's go to symbol. Let's see if this works. Take that integer, to symbol, prepend highlight. All right, let's see. Very good. So now let's just encapsulate all of that. So we'll call that k nearest rotation, I guess. Stick that there. Great, make this a little smaller or a little more vertical. Okay, good. Okay, so now we can call those back. So now we want to format the data for playback before we move on to the next section. In order to do that, we'll want to have a, we'll want to give this a message that's properly formatted. So the playback takes start time, end time, gain, speed, and window. So for the sake of today, we're just going to give it a gain of 1, a speed of 1, and a window of 0.7. The window there refers to the window shape, sort of how trapezoidal it is. It gets more trapezoidal as it approaches 1. 0.5 is a sinusoid, or half of 1. Yeah, so we'll just give it 0.7. So we just need to calculate the start time and end time based on the number there. So for that, all we need to do is multiply by the grain size. So what is that again? It's the third argument, I believe. Oops. Multiplied by the grain size. Let's just make sure that is working. Great. So we'll take this number, we'll multiply it by the grain size. And in fact, we don't need to see that number there. It's just an extra bit of interface that's not necessary. So let's just go straight like that. Just a quick sanity check on this. Good. And now we'll need to do this again, but +1. Oh, a little laggy there. There we go. So that'll be that. So that'll be this. This is start time. This is end time. So now we'll make it so it can play in reverse at a certain point, but it's going to be a long video, so we'll just do the most straightforward thing right now. So we'll do sprint F, and we want, because we're trying to do poly objects, we want note, and then we'll want, what is it? So the first float, the second float, and then it'll just be, for now, we'll just do 1.7. Now I believe that if we just join these two items and send it in here, then we will get our formatted note message. There it is. Okay, so now if we send this to corpus playback, actually instead of that, we're going to do note out here, and then send to corpus playback, and then also just so we can see what's going on, we can do that. Now let's see if it sounds. There it is. Oh, it's 7. It should be 0.7. Hopefully that won't cause any issues. Let's see if that works. Good. Great. Okay, brilliant. So we're getting there. All right, so we want to save this as a, or rather also make a data set, or rather a label. Sorry, that's not what I wanted. We want to give this labels, and we want to also make it into a grid. Let's do the grid first, and then apply the labels. So the grid part is reasonably simple as well. We will want the fluid.grid object, oops. And just like the standardize function above, we'll fit transform once again for a second plotter. Okay, so in fact, I'd like to, do I actually want to copy it? I think I do. I think if I just copy it all out, it'll save me a little time. So I'll take all of this, copy it over here, and I'll have to change some of the names. So dataset grid, kitty tree 2D tree grid. Okay, I'll need another inlet for this tree that's separate. Now, so after normalize, I do need to have trigger bang symbol. So I will refer, fit and refer the data, and then dump it out. And then if I have, oops, a plotter here, like so, and then again going into the new outlet there. I'm not sure what I did to that plotter there. That was weird. Let's see if I can just reanalyze there. Great, and I have a grid version. So the only other thing is the grid sort of looks weird when it's between 0 and 1 because it's right at the edge. So I'm going to go ahead and just do a little, maybe can I reformat the grid? There is a, oh, I can do that with my normalization. So I could do at min 0.05, at max 0.95. Not 0.00, just 0.05. At min and max like that, okay. And I also want the point size to be smaller. So is the KD tree, oh yeah, so we also need the KD tree here to go to my note out here. Now, the right outlet for the plotters, I believe, can actually be shared. So let me actually get rid of that, send this to here, and then hook this up to this. There we go. Great. Okay, great. So now all we have left to do is to do the labels. Which will be useful later on, although won't add anything sort of sonically at this moment, but might as well sort of include it all at this stage. What we have left to do is to add the label set, and then we will be done for this first part. We're going to use k-means, which is a flucoma object. Cluster data points with k-means, so you can see here. Tell it how many clusters you want, and it figures that out. What we're going to want to do that with is the original data set before the UMAP. So we'll use all the data in order to find that. So first let's make the k-means object. So fluid.k-means, and we want the number of clusters to be our fourth argument. So it should be 10 or 5. I have 5 there. And then we want to send in a message. First clear the data, then fit predict, and then the buffer name. So that's going to be the second item in a list that's sent from the fluid.standardize object. And then we're going to want to give a name to a label set that it fills the data with. So we'll just call it the name of the object and then k-means. So we'll need to create that label set as well. Fluid.label set. First argument, k-means. Okay, great. And that doesn't need to be connected to anything. It just can float there. Though we're going to sort of automate a dump on it so that it can populate the plotter. So do trigger bang symbol. So out of here, we will get the symbol there. Great. And then we will want to, right, so already it should come through there. Let's get a test to see if it works. This way. Wait, sorry, no, it comes out of this. We'll need a dump there. So let's see if we already have it working basically. So let's load back in the piano piece and do the analysis. And yep, there we go. Good, we can see that it is labeled all those. If we send the dumps data to the right outlets, this is really plotter 1 and 2. Now if we do that again, or rather if we dump it, it should color it with 5 different colors. There, and there are our labels. Okay, so then how to use these labels, and how to do various things like trying to match timbrely with a live input, that is for a later video. But for now we have this. We have the analysis and the organization and labeling of the data complete. And we can see